on this class discuss the problems on Proell governance. In the last class, we have studied about the topics that are covered for Proell governor and what governor, and finally we get the relation between speed and height of the governor. So what is the formula? We have covered that. That is n square is equals to fm by bm into m plus m by 2 into 1 plus q divided by m into 895 by h. This is the final formula we get it for the Proell governor with respect to the speed and the height of the governor. Now we are going to the problem. Then here it is a problem that a Proell governor has two equal arms of the length 300 mm and the upper and the lower ends of the arms are pivoted on the axis of the governor. The extension arms of the lower links are each 80 mm long and parallel to the axis when the radius of rotation of the balls are 150 mm and 200 mm. And the mass of each ball is 10 kg and the mass of the central load is 100 kg. Determine the range of speed of the governor. Then what is the thing we need to find out is finally range. Range of the governor is nothing but the maximum speed and the minimum speeds. The difference we will call it as a range of the speed. Then for what we are going to solve it is Proell governor. Firstly, we have to find out which type of governor he has asked for and what is the formula to find the relation between governor height and the governor speed. So firstly, we have to note the given data. After that, we have to proceed it to the formula. So then, what is the given data? The Proell governor. Finally, it has given that the Proell governor. Equal arms of length is 300 mm. That means what? The lengths of the governor are of equal. That means arms and the lengths. That means above the line or below the line. That means the DF and PF are equal. That is related to 300 mm. Then one more thing. The extension of the arms of lower links are each 80 mm. The extension means these are all, if you see in the diagram, how the diagram will be. So we have to be carefully draw the diagram like that. So here DF and PF both are of equal lengths, that is 300 mm. Firstly, we have to draw the line diagram. Then after that, what is the main thing? The extension of the lower arm. What is the lower arm? DF. The DF is the lower arm. It has extended to BF. So what is the length of the BF means? That is 80 mm. It was given in the question itself. Then what is the next one is, and it is parallel to the radius, and the radius of the rotation of the ball, that means R. The radius of rotation of the balls, that means R, the speed. Okay, that is 150 mm and 200 mm. So here there is a two radii of rotations. One is R1 is equals to 150 mm and R2 is equals to 200 mm. There we can get it the information that the speed is of varying. Then we need to find out is range of speed. That is in other words, how much of speed is varying. That means minimum speed is how much and maximum speed is how much. The difference we will call it as a range. So here they are given that the radii of rotation is of R1 as 150 and R2 as 200. And mass of each ball. How many balls we are having? 2 balls. But we are going to solve the problem for only half of the section only. So that is 10 kg and mass of the dead weight or central load, that is 100 kg. So by the given data that small m is equals to 10 kg and capital M is equals to 100 kg. Then first of all we have to find out the minimum speeds and maximum speeds of the governor. The minimum speeds may be related to which radius of rotation means r1. Maximum speed is related to the radius of rotation r2. So n1 is equals to minimum speed and n2 is equals to maximum speed. Then what is the radius of rotation, as r1 is equals to, what is the indication, that is fg, that is equals to 150 mm. Then from there we are going to solve this problem in a separate manner. That means two diagrams we need to draw. First one is minimum position and the second one is maximum position. How to variate that? Everything in the diagram is same, but only the difference is radius of rotation, only the difference. So in the first diagram r1 as 150, but in the second diagram R2 as 200 mm. That is only the difference. All the remaining concepts are same. So then we need to find out the height of the governor. So from this height of the governor, what is the height? That is, it will indicate a diagram of triangle FPG. This is the thing. So from this diagram, we need to find out the PG. Then how to find out the PG? PG is equals to, that is a triangular. So right angle triangle. So hypotenuse we need to find out. So hypotenuse is a PF and PG is a, that is. So we need to find out the PG is equals to hypotenuse PF square minus FG square root of. So finally we get the height as 0.26. Then and we need to find out Fm also. So Fm, how much of Fm? Fm is nothing but the B, that is almost a triangle. Okay, so Fm is equals to GD is equals to PG. So that is called the 260 mm or 0.26 meters that we have received. Since why we are equalizing the concept that the arm and the links, the both are equal lengths, so the angle of proportion is also be the same. So that's why Fm is equals to PG. Okay, then Fm is equals to PG. Then in the similar way, we need to find out Bm value. Bm is equals to Bf plus Fm. Well, how much of Bf? That is 80 plus Fm means that we have noted for just now that 260 mm. So totally finally it is a 340 mm. That is simply 0.34 mm. Therefore, we know that the formula for n square. So n1 square, why we calculated the Fm and Bm? So Fm and Bm is in the formula that n1 square is the Fm by Bm into m plus m by m into 895 by h1. There is a concept of Q is there, but for Q, a small notation or indication that when arm length and link lengths are both are equal, then tan alpha by tan beta or tan beta by tan alpha is equals to 1. So the Q will be 0. So these terms will be neglected. Then so substitute the formula FMBM is equals to Fm by Bm is equals to 0.26 by 0.34 into 10 plus 100. Small m is the mass of the ball plus capital M is the mass of the central load divided by small m, 10 into 895 by h1. What is the h1? Height of the governor. Just now we solve or we find out that 0.26. So finally n1 is the 170 rpm. That is the minimum speed. Then in the similar way we need to solve same procedure for finding the N2 also. So in the same procedure for constructing the diagram maximum position. So there only the difference is N2, the radius of rotation only the difference. So by the same procedure, if you follow that, we can get it the N2 as 180 RPM. So N1 minus N2 or N2 minus N1. The only the difference. Previously it is 180 and the next one is 170. So the reference is 10 RPM. This is called the range of the speed. Nextly, in the same way, we can solve it for if the two arms of lengths are not be equal, then we can find out in a different manner. So after that, the concept is Hartung governor. Then the Hartung governor previously in the types of the governors, you know that is a centrifugal governors one model and it is loaded spring type. Okay, this is called the concept of Hartung governor. The Hartnell governor is a spring loaded type governor. It consists of two bell crank levers which are pivoted at the points O and O to the frame that we can see in the diagram or figure. The frame is attached to the governor spindle and therefore it rotates with it. Then each of the lever carries a ball at the end of the vertical arm OB and a roller at the end of the horizontal arm OR. So a spring in compression provides equal downward forces on the two roller through a collar on the sleeve. The spring force may be adjusted by the screwing to a nut up and down on the sleeve. So let us find out the relation that let F is equals to spring force, Fc be the centrifugal force, and m is the mass of the sleeve, and x and y be the length of the vertical and horizontal arms of the bell crank lever, which may be of respectively. So from the diagrams, we can say that the governor in the mid position, by neglecting the effect of obliquity of the arms, by taking the moments about the fulcrum O, we can say that the Fc into x is equals to S into x plus mg by 2 into y. This is the formula or relation between the speed of a governor. So in that Hartnell governor, this is the Hartnell governor. It is a spring-loaded governor. It consists of two bell crank levers which are pivoted at the two arms. Then let us find out the relation that the helical spring in the compression provides the equal downward force on the two roller through a collar on the sleeve. The spring force may be adjusted by the screwing nut on the two rollers through a collar on the sleeve. These force of nut will be results in the results on the down on the down on the sleeve on the governor. Then let us consider, let M be the mass of the each ball, and capital M be the mass of the sleeve, and R1 be the minimum radius of the rotation, and R2 be the maximum radius of rotation, and omega 1 be the angular speed of the governor, which is of minimum radius, and omega 2 be the angular speed of the governor at maximum radius of the governor. So S1 be the spring loaded spring force exerted on the sleeve at omega 1, and S2 be the spring force exerted on the sleeve at omega 2. Then FC1 be the centrifugal force at omega 1, and FC2 be the centrifugal force at the angular velocity omega 2, which is in radians. So S be the stiffness of the spring or force exerted by the compression to compress the spring by 1 meter, and X be the length of the vertical or ball arm of the lever in meters, and Y be the length of the horizontal or the sleeve of the governor, and R be the radius of fulcrum about the O from the governor axis, or the radius of the rotation when the governor is in the mid position. Then consider the forces which are acting on the one bell crank lever. So the minimum and maximum positions, which are all we can see in the diagram. Let H be the compression of the spring when the radius of rotation is changes from R1 to R2, and for the minimum position, that is when the radius of rotation changes from R to R1, that we can show in the diagram of A, and the compression of the spring or the lift of the sleeve H1 is given by the formula, that is H1 by Y is equals to A1 by X, that is equals to R minus R1 divided by X. So consider the forces which are acting on the one bell crank lever. The minimum and maximum positions is shown in the figure. Let H be the compression of the spring when the radius of the rotation of is changes from from R1 to R2. So for minimum position, that is the radius of rotation is changes from R to R1, which will be shown in the figure A. The compression of the spring or lift of the sleeve H1 is given by H1 by Y is equals to A1 by X equal to the H A will be write it as R minus R1 by X. Similarly, for the maximum position, that is when the radius of rotation changes from R to R2, that is shown in the figure B, the compression of the spring or lift of the sleeve H2 is given by H2 by Y is equals to A2 by X, that is A2 we will write it as R2 minus R by X. So by adding these two equations, that H1 plus H2 by Y is equals to R2 minus R1 by X, or H by Y is equals to R2 minus R1 by X. Simply H1 plus H2 we will call it as a H. So H is equals to R2 minus R1 by X into Y. So for the diagram, of minimum position by taking the moments about O. Then we get it from the diagram that mg plus s1 by, that is s1 means spring stiffness, s1 by 2 into y1 equal to fc1 into x1 minus mg into a1. That is, if you see in the diagram, from the diagram for taking the moments about O. So then cross out these two value, that mg plus s1 equal to 2 by y1 into fc1 into x1 minus mg into a1. Again for maximum position also, by taking the moments about O, we get mg plus s2 by 2 into y2 equal to fc2 into x2 minus plus, for maximum means we are have to add it, so plus mg into a2. Finally, from subtracting the equation number 4, that means mg plus s1 minus 5, that is mg plus s2. So s2 minus s1 is equals to 2 by y2 into fc1 into x1 x2 plus mg into a2 minus 2 by y1 into fc1 into x1 minus mg into a1. We know that s2 minus s1 from the diagram, s2 minus s1 is equals to h into s, and h is equals to r2 minus r1 into y by x. So by substituting all these, we can get it that s is equals to s2 minus s1 by h equal to s2 minus s1 into h means r2 minus r1 into y by x. So reversely place up means x by y. By neglecting the effect of mobility of the arms, that is x2 is equals to x1 is equals to x, and y1 equal to y2 is equals to y, and the moment due to the weight of the balls, that is mg, we have for minimum position as mg plus s1 by 2 into y equal to fc1 into x, or mg plus s1 is equals to 2 into fc1 into x by y. Similarly for maximum position also, mg plus s2 is equals to 2 into fc2 into x by y. Here also s2 minus s1 same, s2 minus s1 is equals to 2 into fc2 minus fc1 into x by y. We know that the formula, and the same formula if we substitute there, finally s is equals to 2 into fc2 minus fc1 by r2 minus r1 into x by y whole square. This is the final formula, we have get it there. So after that, the formula where we get it there. Then coming to the problem, a Hartnell governor which is of having a central sleeve spring and two right-angled bell crank levers and moves between 290 rpm and 310 rpm for a sleeve lift of 15 mm, and the sleeve arms and ball arms are of 80 mm and 120 mm respectively, and the lever are pivoted at 120 mm from the governor axis, and mass of the each ball is 12.5 kg, and the ball arms are parallel to the governor axis at the lowest equilibrium speed. Determine the loads on the spring at the lowest and the highest equilibrium speed, and second one is stiffness of the spring. So from the given data, we collected that N1 is equals to 290 rpm and N2 is equals to 310 rpm. So we know that the formula omega and omega to omega 1 based on the n1 and n2, 2 pi n by 60. So collect the data from there. We get it the omega 1 as 2 pi n into 2 pi into n means 290 rpm, and that is finally 30.4 radians per second, and n2 based on n2 we get it that n2 omega 2 is equals to 32.5 radians per second, and h is the 0.015 meter, and y is equals to 80 mm, and x is equals to 0.12 meter, r is equals to 0.12 meter, and finally m is equals to 2.5 kg. So what the thing we need to find out is determine the loads on the spring at the lowest and highest equilibrium speeds. So S is the spring load at the lowest equilibrium speed, and S2 be the spring load at highest equilibrium speed. So since the balls arms are parallel to the governor axis at the lower equilibrium speed, that is at n1, that is 290 rpm as shown in figure A. Therefore r is equals to r1 is equals to 0.12 meter, and we know that the centrifugal force for minimum speeds, that is fc1 is equals to m omega 1 square r1, that is m means 2.5 kg, omega means 30.4 whole square into r1 is equals to 0.12. So finally fc is as 277 newton. Now let us find the radius of rotation for highest equilibrium speeds, that is at n2. N2 is 310 rpm. So finally the position of all ball and arm sleeves at the highest equilibrium speed that we can see in the diagram. That r2 is equals to radius of rotation at n2 is equals to 310 rpm. That we know that h is equals to r2 minus r1 into y by x. That r2 is nothing but r1 plus h into x by y. So substitute there 0.12 into 0.12 plus 0.015 into 0.12 by 0.08 into 0.1425 meters. So all the values are to be kept in the meters only. The centrifugal force at maximum speed means fc2. Finally m omega 2 square into r2. M means 2.5, omega means 32.5 whole square into r2 means 0.1425. So finally we get it that 376.6 Newton. So by neglecting the here, if you see from these diagrams, by neglecting the obliquity effect of arms and links and moment due to the weight of the balls, we have for lowest position as mg plus s1 is equals to 2fc1 into x by y, that is equals to 2 into 277 into 0.12 by 0.08, that is finally 831 Newton. So S2 is equals to 831 Newton. Similarly for highest positions also, we need to find out that mg plus s2 is equals to 2fc2 into x by y. So finally s1 is equals to 1128 Newton. So finally stiffness formula is S is equals to S2 minus S1 by H. So we know the value of H, we know the S2 as 1128 minus S1 as 3831 by H is nothing but 15. So the stiffness of the spring is 19.8 Newton millimeter. So after that we go for the sensitiveness of the governor. Sensitiveness means it is the ability of the governor to withstand the maximum weight or load. So the sensitiveness of the governor is considered two governors which are of A and B at same speed. When the speed increases or decreases by a certain amount, the lift of the sleeve of the governor A is greater than the lift of the sleeve of the governor B. It is to be said that the governor A is more sensitive than the governor B. In general, the greater the lift of the sleeve is corresponding to a given factorial change in the speed. The greater is the sensitive of the governor. The sensitiveness is defined as the ratio of differences between the maximum and minimum equilibrium speeds to the mean equilibrium speed. So let us consider N1 be the minimum equilibrium speed and N2 be the maximum equilibrium speed. So mean speed is equals to N1 plus N2 by 2. So finally sensitive is it is a very important 2 marks question. So sensitiveness is equals to ratio of differences of the speeds by mean equilibrium speed. So N2 minus N1 by N. Simply we can write it as 2 into N2 minus N1 by N1 plus N2. Simply we can write it with respect to angular velocities also, the both are same, since omega is equals to 2 pi n by 60. We can replace the n with omega. So 2 into omega 2 minus omega 1 by omega 1 plus omega 2. This is a very important question for 2 marks. Then stability of the governor. The governor is said to be stable when for every speed within the working range there is a definite configuration, that is there is only one radius of rotation of the governor, the balls at which the governor is in equilibrium. So finally only one radius of rotation of the governor for equilibrium condition. For stable governor, if the equilibrium speed increases, the radius of governor of the balls must also be increases. Then a governor is said to be negligible if the radius of rotation is decreases as the speed may be increases. So this is the main difference. Then isochronous governor. The governor is said to be isochronous when the equilibrium speed is constant. That is the range of speed, that means the difference between the speed n2 minus n1 or n1 minus n2 is 0 for all the radii of rotation of the balls within the range of working by neglecting the friction. Let us consider in case of a Porter governor which are of running at the speeds n1 and n2, that is minimum and maximum. The formula is n1 square is equals to small m plus capital M by 2 into 1 plus q whole by m small m into 895 by h1. Similarly, h2 also. For isochronous governor, the range of speed should be 0. So n1 minus n2 or n2 minus n1 is equals to 0. Therefore, from this equation, h1 is equals to h2 or n1 is equals to n2, which is impossible in case of Porter governor. Hence, the Porter governor cannot be a isochronous governor. Then now consider for Hartnell governor. Just now we discussed about the Hartnell governor. The formula is capital mg plus s1 equal to 2 into fc1 into x by y equal to 2 into m omega square r into x by y. fc1 means centrifugal force, so it is m omega 1, that means 2 pi n by 60 whole square into r1 into x by y. Similarly, for speed n2 also. For isochronous governor means the range of speed is 0, that means n1 is equals to n2. So finally we get it that mg plus s1 by mg plus s2 equal to r1 by r2. But actually in practical it is not possible of isochronous governor. So because of the sleeves will move to the one of the extreme positions immediately when the speed difference is occurs. So that is may not be possible of isochronous governor. Then last one is hunting. So the hunting is said to be the speed of the engine fluctuates continuously above and below the mean speed. That means we in the bikes we can call it as a jerks. Okay, jerk means the speed, constant speed. That means the below or above the constant speed. The governor is set there. How it is possible means either the supply of the fuel is more or the lesser than the requirement. So the governor is said to be hunt if the speed of the engine fluctuates continuously above and below than the mean speed. It is caused by two sensitiveness of the governor which may changes the supply of the fuel by a large amount when the small change in the speed of the rotation is takes place. For example, when the load of an engine is may increases, the engine speed maybe decreases, and if the governor is very sensitive, the governor sleeve immediately falls to its lowest position. This will result in the opening of the controller valve that will supply the huge fuel or excess fuel to the engine than the requirement, so that the engine speed will be changes rapidly again and again, and it may reaches to the highest position also. Due to this moment of sleeve, the controller valve, it will cut off the fuel supply to the engine, and thus engine speed begins to fall once again. This cycle may be repeated indefinitely. Such governor may be admitted either by maximizing or minimizing the minimum or maximizing the fuel amount, and the effect this may causes for the wide fluctuation of the speed of the engine. So the engine will call it as a hunt. Then effort and power of a governor. The effort of a governor is mean force exerted at the sleeve for a change of the speed. Effort means it is the mean force exerted by the sleeve for a given change of speed. That is called the lift. It may be noted that when the governor is running steadily, there is no force at the sleeve. But the speed changes, there is a resistance at the sleeve which opposes the motion. Then the power of a governor is the work done at the sleeve for the given percentage of change of speed. So effort and power are both are interrelated. The effort of the governor is mean force exerted at the sleeve for a change of and the power is the work done at the sleeve for a given percentage of change of speed. So by mathematically it is shows that power is equals to mean effort into lift. Okay, so for different governors we can get it the formula for the relation between the power and effort. So power is nothing but the mean effort into lift of the sleeve. For Porter governor, how much of the speed increases or changes? Okay, this is the formula. we get up there. So both the concepts of this variation of effort and the power will be vary. So finally, for 2 marks, it is very important to note up the sensitiveness of the governor, hunting of the governor, isochronous governor, and the effort and power of the governor. So in these four, importantly we have to study what is governor, classification of governor, sensitiveness of the governor, isochronous governor. These are the four questions we can expect for 2 marks. So with that we can completed this governors topic. So mostly we have to remember for thoroughly derive the equation for relation of H and N for Porter and Proell and Watt governor. These are the main three, and Hartnell also. So these are the main four, or basically we first read the problems on Porter and Proell, both the derivations also. Okay, then thank you.